Welcome to AI Paper Slop, the YouTube series, where we break down the latest AI and tech papers for researchers and ML engineers. Today, we are looking at a fundamental bottleneck in AI, which is that reinforcement learning for agents requires just way too many costly environment interactions to be practical for real-world tasks.
Right. Yeah, the sample inefficiency is just brutal.
Exactly. So today's paper is called Sample Efficient Learning from Agent Experience by Chen-Wei Gu and colleagues from Monash University and ByteDance. And the core insight straight away is this. While in-context learning, or ICL, solves that RL sample inefficiency by letting models learn from trial and error, like right in their prompts, those gains completely vanish the second the context window clears.
Total amnesia, yeah.
Right. So this paper introduces a breakthrough called Experience Distillation, or EPD. And by using one-step branched rollouts, it basically distills those temporary ICL gains directly into the model weights with zero additional environment interactions.
Which is huge.
It is. It matches classical RL baselines like PPO and GRPO,
Right.
while using up to, get this, 57 times fewer environment samples.
Yeah.
So if you are building agents for long horizon tasks like software engineering, this paper is a blueprint for drastically cutting your compute costs.
Yeah, because the current paradigms for training agents on these complex tasks, they basically leave us trapped between two deeply flawed extremes, you know?
Yeah.
We're constantly trading off between retaining capabilities permanently and the sheer financial cost of getting the data to actually do that.
I mean, if you're listening to this and you've tried to scale an RL pipeline for a software agent, you are probably screaming at your dashboard right now about sample inefficiency.
Oh, so, okay.
Because RL is brilliant if your environment is cheap. Like go self-play or having an agent solve lightweight coding puzzles. Fine. Spinning up millions of simulated interactions is just server cost.
It's just a compute bill, yeah.
Right. But think about what happens when the task gets real. Say you want an agent to navigate a 100,000-line code base to patch a security bug, or, I don't know, synthesize a new battery material in an automated lab.
Or drafting legal analysis that needs human review.
Exactly. You physically cannot run a million episodes of that. The feedback loops are just way too slow, and the sample counts that RL demands become completely impossible.
Right. The barrier to entry isn't just compute anymore. It's the physical or logical cost of a single rollout. So because we can't afford millions of RL episodes, the whole industry has essentially pivoted to in-context learning as a crutch.
Yeah, the ICL crutch.
You take a frontier LLM, give it a scratch pad, let it attempt a task, fail, read the compiler error, and try again. And the sample efficiency there is phenomenal.
It's amazing.
It adapts instantly because it's holding all that interactive evidence right there in its working memory.
But the open secret here is that ICL is essentially just cramming for an open book exam.
That is exactly what it is.
Like, you perform spectacularly in the moment, but the second the exam is over and that context window clears, you forget everything. The underlying model parameters haven't shifted at all.
Not by a single decimal point.
Total amnesia. So looking at this problem, my immediate thought, and probably everyone listening who has built an SFT pipeline is thinking this too, why not just collect all those successful trial and error runs, filter for the winning trajectories, and just do supervised fine-tuning on them?
Well, the authors actually anticipated that exact instinct and tested it. They collected successful trajectories across 749 curated SWE bench software tasks.
Okay.
When they ran standard SFT on just the successful outcomes, the model only recovered 3.8% of the performance gains that ICL originally achieved.
Wait, 3.8%?
Yeah, it was basically a statistical flatline.
That is practically a rounding error. I mean, I guess SFT is essentially just behavior cloning on the final answer, right?
Precisely.
If ICL is the open book exam, SFT is like trying to learn multivariable calculus just by reading the final correct answers at the back of the textbook.
Right, without ever seeing the scratch pad work.
Exactly. You are exposing the model to the what, but you're totally starving it of the how or the why. It misses the reasoning of how the agent recovered from those initial failures. So we need a way to bake the full contextual journey into the weights, which conceptually brings us to context distillation.
Right. Context distillation is the logical next step here. Conceptually, you train a student model, which starts with a blank context, to mimic a teacher model that is fully loaded with that trial and error context.
Sounds great in theory.
The student learns to output the high-quality actions without the massive prompt, but the roadblock is generating the training targets. To distill a teacher that is conditioned on experience, you normally have to run that teacher in the environment again.
So it can generate new actions.
Exactly, to train the student on.
But wait, that means you're back to paying the environment tax. You just destroyed the sample efficiency you were trying to save.
Exactly. And we see teams try to bypass this all the time with model-based RL. They take an LLM, prompt it to act as a simulator or a world model, and just pretend it's the environment.
Right, so they don't have to touch the real one. But the paper dissects why this fails for long horizon tasks, right?
Beautifully. The issue is cascading hallucinations. Even in simple text adventure games like the Tail Sweep benchmark, the world model just loses the plot. The errors compound exponentially over long rollouts.
I saw this in the paper. The authors found instances where the LLM, acting as the world model, just started fabricating arbitrary rewards.
Yes, like giving the agent 10 points for dancing in a closet.
10 points for the closet dance. I mean, it's funny, but that completely poisons your training data. The model starts embedding the policy's desired actions directly into the environment's observations.
The boundary between the agent and the physics of the world just evaporates.
So if the real environment is too expensive and a simulated environment hallucinates us into a closet dance, we are trapped. How does EPD get around this?
This is their algorithmic breakthrough. It's powered by what they call one-step branched rollouts. Instead of simulating a multi-step trajectory into the unknown, you anchor everything to the past.
Okay, walk me through that.
You take a recorded history from your initial ICL logs, you step through that history, pick a specific branch point, and let the context-aware teacher generate just one single action.
Just one.
Just one. And then you immediately stop. No world model. You don't touch the real environment. You just optimize the student model's weights to match this one action using a forward KL divergence objective.
Wait, I need to push back on the mechanics of this.
Yeah.
Because if we only predict one step and then hard stop, how is the student model learning a cohesive sequence of behaviors? To plan a long horizon task, doesn't it need to know how the environment reacts so it can plan the next step?
Well, you only need to know the environment's reaction if you are trying to explore new state spaces. But here, we aren't exploring, we are distilling an already successful path.
Oh, I see.
You evaluate the teacher's single action against the recorded environment responses from the original logs.
Right.
The teacher looks at the trajectory up to step T, thinks about what to do next based on its context, and you train the student to match that exact probability distribution for step T. Then you reset, move to step T plus 1 in the log, and repeat.
Okay, conceptually, that is incredibly elegant. You're distilling the localized thought process at every single node without ever needing to see the future.
Exactly. It chains together naturally.
But practically speaking, if you're working with an 80,000 token context window, which is standard for these heavy software tasks, and you have to feed in 79,000 tokens of history just to get the teacher to predict one single action token.
Yep.
And then repeat that separate process for every step in a 500-step trajectory. Your supervision density is essentially zero.
It's terrible.
The compute required to endlessly reprocess those massive overlapping prefixes would melt your GPU cluster. You just traded an environment bottleneck for a compute bottleneck.
You did. And that compute bottleneck is exactly why this naive context distillation hasn't been widely adopted before. Processing overlapping prefixes is astronomically wasteful.
So how did they solve it?
They engineered a system called branch packing. Instead of treating every branch point as a separate training example, they pack multiple teacher decisions from successive branch points of the same trajectory into a single contiguous training sequence.
Okay, I want to make sure everyone listening can visualize this. It's kind of like carpooling on a long road trip, right?
What do you mean?
Like instead of 4 people taking 4 separate cars from the exact same starting point, driving the exact same highway route just to get off at 4 consecutive exits, you put them all in one car, you drive the route once, and let them out one by one at their stops.
Yes.
You only pay for the gas, or in this case, the attention mechanism compute once.
That is a highly accurate mechanical analogy. By using causal attention masking, they process the shared historical prefix once, and then compute the losses from multiple subsequent actions in a single forward pass.
Wow.
The efficiency gains are staggering. On the Tail Sweep benchmark, branch packing compressed 4,096 separate training examples down into just 128 packed sequences.
That's insane.
It dropped the required training steps from 768 down to just 64.
So that is a greater than 10x speed up in total wall clock time. But let me challenge the math here for a second. We are dealing with strict objective functions. Equation 2 in the paper defines the distillation objective based purely on the exact recorded history.
Right.
If you pack previous teacher generations into the same sequence to predict the next step, doesn't that technically corrupt the context? It's now got slightly divergent teacher outputs instead of the pure log.
You've highlighted the exact trade-off they made. Yes, branch packing introduces a slight deviation from the pure mathematical objective. It is a practical approximation.
Does it hurt performance?
No, the empirical results show this theoretical noise actually acts as a regularizer. The packed approach slightly improved the retained ICL gains, pushing the retention rate from 84.2% up to 90.1%.
So the computational savings are massive, and the model actually learns better. That's a huge win. And they layered a few other optimizations on top of this, right? The one that stood out to me was enhanced teacher reasoning.
Yes.
It sounds deceptively simple. They just prompted the teacher model to think longer and generate a deeper chain of thought before emitting the final action. But on the complex detective task, that simple change raised their normalized score from 50.7 all the way to 71.8.
Because the student model isn't just mimicking the final API call or line of code, it is learning to mimic the reasoning trace itself.
The actual internal monologue.
Exactly. If you force the teacher to reason more thoroughly about the trial and error context, like analyzing why a previous action failed, the student absorbs a much richer logic path. And another thing, they proved you don't even need to store the full distribution logits for distillation.
Wait, really?
Yeah, standard next token prediction works just as well.
Oh, wow. Which saves a massive amount of memory. You don't have to store a 100,000 dimensional probability vector for every single token across an 80K context window. You just need the chosen tokens.
Exactly.
So we have a method that bypasses the environment tax and an optimization that bypasses the compute bottleneck. Let's talk about how this actually stacks up against the heavyweights, because looking at the PPO baseline in this paper is almost embarrassing.
The benchmark results on those 749 SWE tasks are highly revealing. To set the ceiling, ICL, with the full trial and error context in its prompt, gets a 76.4% pass at one rate. EPD, where the student has zero context and relies purely on its weights, gets 51.4%.
So it permanently baked in 64.8% of the temporary ICL gain.
Right.
And then we look at standard reinforcement learning. PPO only hit 17.7%. Let that sink in. 17.7 versus 51.4. And the sample efficiency difference is crazier. EPD reached that 51.4% using 9.6 times fewer environment samples than PPO needed just to hit its miserable 17%.
And the performance gap widens on the tail suite text games. EPD scored an impressive 43.8. GRPO, which is the absolute darling of the reasoning community right now, only hit 29.9.
Wow.
And EPD achieved that superior score while using 57.2 times fewer environment samples than GRPO.
57 times fewer samples. I mean, I have to imagine part of that is because GRPO just physically cannot explore a complex environment effectively. Why does GRPO fail so spectacularly here? We throw massive compute budgets at best event sampling. Shouldn't eventually find the right path.
So to understand that, the authors ran a brilliant diagnostic experiment called the color button task. GRPO relies heavily on on-policy sampling. It learns by trying actions based on its current internal probabilities.
Okay, makes sense.
Imagine a task where the correct sequence is a highly specific passcode, red, then green. If the model's natural inclination doesn't randomly stumble upon that exact sequence, the environment returns a reward of 0.
So even if you scale your batch size and sample 256 trajectories.
If none of them randomly hit red, green, every single sample gets 0 reward.
Which means the gradient is flat. GRPO gets 0 learning signal to update its weights, no matter how much compute you burn. It's essentially blindfolded darts.
Precisely. Increasing the group size in GRPO doesn't force systematic exploration. It just takes more granular samples from the exact same initial distribution.
Right.
EPD succeeds because it bypasses this bottleneck. It relies on ICL during initial data collection. ICL lets the agent read its past failures in the prompt, systematically eliminate them, and logically reason its way to the correct sequence.
And once ICL finds the needle in the haystack, EPD distills it into the weights.
Exactly.
This highlights a crucial divergence in distillation techniques. The paper uses forward KL divergence. A lot of practitioners might wonder why they didn't use reverse KL, which is also known as on-policy distillation, or OPD. Why did reverse KL fail?
The mathematical intuition is key here. With forward KL, the teacher's distribution acts as the ground truth target. The student is constantly anchored to the teacher's successful recorded path.
But with reverse KL?
With reverse KL, the student is forced to sample its own actions first, generating trajectories without the benefit of context, and then the teacher tries to grade those blind trajectories.
And because the student is flying blind, It immediately makes suboptimal choices that push it completely off the manifold of the recorded data.
Exactly. And once it falls off the manifold, it enters regions of the state space it has never seen before. The authors observed OPD models literally getting stuck in endless loops of hesitation.
Like what?
The student would realize it was lost and start outputting loops like, wait, maybe read paper. Wait, no, take paper, wait.
That's hilarious, but also terrible.
It loses all confidence and paralyzes itself because it lacks context for that out-of-distribution space. Forward KL avoids this entirely by using the teacher to drive generation on the correct path.
So it beats the RL baselines mathematically, but let's talk applicability. Does the model actually internalize generalized logic, or is it just memorizing the syntax of the training set? Can it apply these lessons to ODE tasks?
It generalizes exceptionally well. They evaluated the EPD model on 494 completely out-of-distribution software tasks, including entirely unseen code repositories. The pass at one rate improved from a zero-shot baseline of 4.62% up to 8.84%.
That proves it's extracting generalized problem-solving capabilities, not just overfitting.
Right. And it isn't a one-off trick. They tested continual EPD. By taking the EPD-trained model, using it to collect new ICL trajectories, and distilling those back into the model over 5 sequential cycles, they raised the tail suite score from 7.1 all the way to 47.0.
The capabilities genuinely compound over time. But to make this concrete for the engineers listening, let's look at the qualitative case study on Mapster2 repository. It was a bug involving a React UI component, right?
Yeah, this case study perfectly isolates the power of EPD. The task was fixing a filter reset bug. The zero-shot baseline completely failed because it neglected to emit an explicit value null reset when the UI component deactivated.
It just left stale state hanging around.
Exactly. So during the ICL phase, the agent tries that, runs the test suite, and sees an error log showing the filter hasn't cleared. Over 6 interactive trials in the prompt, the agent realizes 2 things.
Okay, what were they?
First, it needs to code that explicit null reset in the UI component. Second, and more importantly, it looks at the downstream query epic, the data pipeline handling API requests, and realizes the pipeline is hard-coded to filter out falsy values.
So even if the UI emits a null, the pipeline drops it.
Exactly. The agent systematically reasons through this and fixes both sides. It adds the UI emission and updates the pipeline propagation to allow the reset signal through.
It absorbed a complex cross-component architectural fix. It traced a UI event all the way through a downstream data pipeline.
Yes. And here is the mic drop. They took the EPD-trained model and evaluated it zero-shot on that task, meaning they gave it the bug, but without the 6 trials of context and test logs.
Yeah.
It perfectly executed that exact UI-to-query logic on the very first try.
No way.
It permanently internalized a highly specific, multi-layered repair pattern simply by distilling its own past epiphanies.
That is profound.
Yeah.
It didn't just memorize the syntax of a patch. It absorbed the architectural logic purely by analyzing its own past scratchpad work.
Exactly.
So let's bring this all together. Experience distillation allows us to take the massive sample efficiency of ICL, that unique ability to logically trial and error your way to a solution in the prompt, and permanently bake it into the model's weights.
Right.
By utilizing one-step branch rollouts and branch packing, it completely sidesteps the massive compute costs of standard RL, avoids the hallucination traps of simulated world models, and completely cures the amnesia of in-context learning.
It elegantly bridges the gap between our 2 flawed extremes. You get the systematic exploration efficiency of an in-context agent paired with the permanent low inference cost capability retention of a fine-tuned model.
Which leaves us with a final, slightly provocative thought for everyone listening to mull over. We've seen that agents can autonomously trial and error their way to success via ICL. Now we have a proven compute-efficient method to permanently internalize those lessons via EPD without any human intervention.
That's a big shift.
Are we approaching an inflection point where AI models can independently self-improve in the wild? Could algorithms like EPD eventually render massive human-curated data sets and external reward models completely obsolete for long-horizon task training? It's like engineering a student who doesn't just cram for the open book exam, but actually learns how to author the textbook themselves.
Well said.
Thanks for joining us on this deep dive into the literature here on AI Paper Slop. Keep experimenting, and we'll catch you on the next one.